a little bit deliberately because we have not completed with this particular derivation yesterday. So this is the part which we were discussing, reflection of light at a plane surface and actual proof of laws of reflection using wave theory of light. So to quickly recap, this is the diagram which we had yesterday. I gave you the details about the diagram, so we can quickly go through those particular details, especially about this particular part, the hemisphere wala part, which I have already discussed, that when A and B, both of them get reflected, there is a simultaneous reflection of each and every particle on that particular wavefront, which causes secondary wavelets to appear, and the secondary wavelets are in the form of hemisphere, that is the semicircles which we have. Then we have already established the distance between them and how the radius of those hemispheres go on gradually reducing, and ultimately we have established this particular point which is very important, that AE and BC, both of them, they are equal, and what will be the length of both of them? It is equal to V into T. Then we went on to discuss some additional mathematical part which is not given, but it is required for us in order to understand these two angles, the angles which are given over here, angle I and angle R, how these are considered to be angle of incidence and angle of reflection. So that is the part we have already seen yesterday. So this is the first part about how ECA is equal to R. That is what we have seen. And in next slide, we have seen how BAC, it becomes I. So how this angle is equal to the angle of incidence. So till this point, we have completed our part yesterday, and we will be continuing our derivation from this point onwards. So keeping in mind these 2 points which we have already discussed, how I and how R are actually given for these particular angles. So moving forward, let's take this derivation further, and now we will be able to complete this particular derivation. So again, the diagram, it remains same as that of before. So this is the diagram on which we are going to understand our discussion. So in this particular diagram, now what we are going to do? So now we are going to consider 2 triangles. Okay, which triangles are we considering? ABC and AEC. So which is triangle ABC? So this is the triangle ABC. We have already considered this triangle before. So this is one triangle which we have. And second triangle which we are considering, that is triangle AEC. So this is one triangle ABC, and another triangle we have this C, E and A. So these are the 2 triangles we are considering. Sorry. So for these 2 triangles, what we have, let's start with AC. Now if you look at this particular diagram, 2 triangles, the AC is common line, or we can consider the hypotenuse of this particular triangle. So it is common. We know, we have already established that AE is equal to BC. We have already seen this AE is equal to BC. कितना है ये VT, ये हम लोगों ने शुरू में किया था. So we already know that these 2 lines are also equal. So based on these, we can say that triangle ABC is congruent to triangle AEC. If you want, we can consider additional part as well, that we have angle over here which is 90 degree plus 2 lines. So you can consider it as a right triangle theorem, jo bhi hai geometry ka. So we know that these 2 triangles are congruent. So if these 2 triangles are congruent, means equal, everything related to these 2 triangles will be equal. Matlab kya? Means we can write angle AEC, angle ACE. So this angle ACE, this angle is equal to angle BAC. But BAC कितना है? I है. Similarly, we can write ACE and PAE are also equal. So this is angle once again ACE and angle PAE. This PAE, that is also equal. R ये हम लोगों ने already established किया था. So from 1 and 2, we can write simple angle of incidence is equal to angle of reflection. So this is the most important law. We can say it's a second law of reflection, which is proved. Any doubts in this? Bolo re yes or no? Okay, good. So this is the derivation which we have started in yesterday's lecture. So this is one law which we have completed. Angle of incidence is equal to angle of reflection. सुजल क्या हुआ? सुजल डाउट है? Okay. Now, from the same diagram, now we can write some other things as well. We can consider some couple of things as well. Okay. What are some couple of things which we are going to see? सबसे पहले तो first point, we can see that incident ray, normal, reflected ray, they are all in the same plane. They are in the plane of paper, which is the another law of reflection. We know that all of they lie in the same plane. Second, also we can write from this that the size of object is equal to the size of image. ये कैसे पता चला? C, AB is equal to C. AB क्या है? It's the incident wave front. मतलब assume करो एक incident object है. And reflection कैसा मिला? CE. That is the reflected wavefront which we have, means the reflected image. Now we have already established that AB is equal to CE because the triangles are congruent. So size of object is equal to the size of image, which we know which takes place in case of a perfect reflection, or to be precise, regular reflection. Another point what we can write from this particular diagram is the lateral inversion. Lateral inversion means what? A becomes left becomes right, right becomes left. So we know that when point A hits, B is still at this particular point. So when point B it comes over here, A has already created a semicircle and it goes something like this. So whatever line you have, that line gets flipped. So AB becomes CE, means A comes to the position of C and B then goes to the position of E. Okay, so the part is flipped. Sorry, A comes to the position of E and B comes to the position of C by undergoing this change. So we know that the part is flipped. We know that A is on the right side and B is on the left side. So A to E, it is on the left side, and B to C, it goes on the right side. So A becomes E, matlab right side becomes left, and left becomes right. That's why we get a lateral inversion. Okay. Now, any doubts till this particular point? Bolo yes or no? Okay, good. So to conclude, based on this particular concept of wavefront, to be precise, the wave theory of light, we have already established that angle of I, angle of incidence, angle I is equal to angle R. That is one law of reflection. Plus, additionally, we were able to observe and we were able to prove the remaining laws of reflection and the additional associated concepts related to that reflection. Now, the most important thing to note over here that the reflection which we are considering is the complete reflection, and the reflection is from a plane smooth surface, means the reflection is a regular reflection. So, with this, we are done with the part of derivation about reflection of light. Okay. Now, just to back up a little bit, what we have started in this particular chapter, we have started with the basic concept of light, nature of light. Okay. Now, we are going to focus on the wave nature of the light. So, in case of the wave nature of the light, we have seen the Huygen's principles. We have seen the concept of wavefronts. We have used this concept of wavefront in understanding the reflection part. Now, the next part is what if we have multiple wavefronts? Means if light it acts as a wave, means whatever we have studied in wave motion must be applicable over here as well. So what if multiple waves they come in contact with one another? Then we know when two or more waves they overlap with one another, they combine with one another, the concept is what we call it as a superposition of waves. Now, since this we already have seen, we can go a little bit faster. We have seen the same concept in your wave motion, chapter wave motion. The same concept I have over here, but still for our simplicity, I'm going to repeat this particular concept. Okay, so by chance, if you have missed it over there, I'll repeat it once again over here. The concept remains same. It doesn't make any difference whether the wave which you're considering, whether it is a mechanical wave as in the wave on a rope, or whether the wave which we are considering something like the wave of light. Now what happens in case of superposition? एक छोटू सा statement है हम लोगों को, ठीक है? This is एकदम छोटू सा tiny सा statement है. This is what we call it as a superposition of a wave. So when two or more waves, there are conditions applied. Obviously, they should travel in a same medium. They are going to pass through a common point, presumably. Now, when they pass through common point, what happens? Each wave is going to create its own displacement. Now, this we already are aware, but still I'm repeating. And that displacement will affect the displacement of another wave. So the resultant displacement at that specific point is actually the vector sum of the displacement due to the individual wave at that specific point at that specific instant of time. Now this is the statement which we have. We have already seen the details of it. Okay. Now in simple words, superpositioning, we call it as overlapping. So when the waves they overlap, what happens? The waves they algebraically add to form a comparatively bigger wave with a higher resultant displacement. Now that higher displacement is a result of the simple algebraic addition. The algebraic sum of all the displacement is what we get as a net displacement or a resultant displacement. Now, depending on the type of wave, or to be precise, what phase the wave is in, we get different types of superposition. Now, one of the pictures I already have shown you, this is the general idea about superposition of the waves. Now, we have two types of superpositioning, giving us two different types of interferences. We have already seen. This is one of the pictures. Obviously, you can check. This is from your previous chapter itself. The same is applicable over here as well. This is something which we call it as a constructive interference. Now, when do we get a constructive interference? See, we are considering a transverse wave. I hope you know that this part, which is in upward direction, isko bolte hai crest. So we are only assuming crests of two waves which are traveling in opposite direction towards one another. So when the crest, they come closer and they meet one another, you can see this part which gives us the addition of both of them. So what happens? The amplitude increases. You already are familiar with everything. That's why we call it as a constructive interference. Vice versa, exactly opposite to this, we have already seen the next type of interference where both of them cancel each other out. This is what we call it as a destructive interference. So we can see over here, we have one crest and one trough. Again, two waves that are traveling towards one another. One a crest, another a trough. So when a crest and trough, they overlap with one another, they superposition with one another, what happens? Both of them, they want to cancel each other out, giving us a flat line, if you see over here, with zero amplitude. And when they move forward again, crest becomes crest, trough becomes trough. So since amplitude becomes zero, we call it as a destructive interference. And I hope I have shown you this some particular GIF as well. So if you look closely over here, now when the two crests, they come closer, you can see. Okay, hey, GIF pause over, yes or no, please, quickly. So if you look over here, when a crest comes in contact with a crest, you can see the magnitude is increased. But now when a trough and a crest, they come in contact with one another. So here we have a crest and here we have a trough. You can see the magnitude, it becomes zero. So this is what we have as a destructive interference. And even the other way around, a trough and a crest. So here we have a trough and here we have a crest. Again, it becomes zero. A crest and a trough, it becomes zero. So ये हो गया destructive. Crest और trough जब आएगा तब क्या मिलेगा हम लोग को? We have a crest and a crest. Magnitude बढ़ा, trough and a trough. Again magnitude भी बढ़ा on other side, no doubt, but again it is increasing. So this is what we call it as a superposition of waves. Any doubts in this? We have already covered this part in wave motion, but since it is needed, I'm again covering it so as to give you some idea about it. Okay, good. Now moving on to the very important point. and a very important part in this particular chapter. We are going to understand something about interference of light. Now, the interference, constructive and destructive, which we have seen, this is applicable over here. That's why I went through entire superposition of waves once again in order to give you the understanding about constructive and destructive interference. Okay. Now, what do you mean by interference of light? Okay. See, what happens in case of interference? Something which we have already seen. See, in wave optics, what we consider light is a wave. Now, which type of wave it is? It's a transverse wave. So, what's going to happen when two waves they overlap with one another, or superposition with one another, or combine with one another? What's going to happen? Obviously, either constructive or destructive interference is going to form. Now, constructive interference form ho raha hai means what? Amplitude is increasing. Now, we know that amplitude is directly proportional to intensity. So, means amplitude is increasing in constructive interference. The intensity of light will also increase. And vice versa, in the destructive interference, the intensity of light will also decrease. So, this change in intensity of light is what we call it as a interference of light. And this is the same which is given in your definition. Now, if you read this particular definition carefully, you can find out what is interference. It's the modification in the intensity. Modification bolo, redistribution bolo, change bolo, it's one and the same thing. The amount of light, the brightness and darkness is what comes in the picture in interference. So whenever we say we are able to see an interference pattern, means what we are going to see exactly a bright spot and a dark spot. So either it will be high intensity, very high intensity, or low as in zero intensity. That is what we call it as a interference pattern or interference in case of a light. Okay. Now, how the interference exactly looks like, that is what we are going to see later. For the time being, let's focus on this picture over here. Okay. Now, since you already are aware of it, we can go a little bit faster. Just let's understand what exactly we have over here. Now, you can see that there are two sources, okay, S1 and S2. Now, as you can see in your diagram, both of them are named S1. So, एक S1 है तो दूसरे को अपन S2 यहाँ पे कर लेते हैं. Okay, वो book में बाद में change कर लो तुम लोग. So, we have two sources of light. Okay, S1 and S2. Now, here, even though they are saying water waves, we can use the same analogy for light. That's why I'm saying sources S1 and S2 are sources of light. ये water पे कैसा आता है? I do have that. I'll show you later on as well. Don't worry. So what happens in this case? If you look closely, you have some continuous lines and you have some dotted lines. Okay, alternate continuous and dotted lines. So what these continuous lines they represent basically? Continuous lines represent a crest, and a dotted line, it represents a trough. So you have alternate crests and trough. For, let's say this is S2, same will be applicable in case of S1. So we have a crest, again followed by a trough, followed by another crest, followed by another trough. So what happens in this case? You see those blue dots which are shown, they are constructive interference, and the red dots which are shown are destructive interference. Now we already know when in constructive interference it forms. So let's focus on this dot over here. Constructive interference, when it is formed, when two crests overlap. So here we have one crest and here we have another crest. That's why here we are getting a constructive interference. If two troughs overlap, again we get constructive only. So here is one trough, here is another trough. So this is again a constructive interference. So if you look, all the blue points, they are the superposition of either two crests or two troughs, giving us the constructive interference. Means what? The intensity is high. Now look at this red point over here. Or any red point for that matter, but let's consider this red point which we have. Now this red point is formed due to the superposition of a trough and a crest. So when a trough and a crest overlap, you get a destructive interference. Or if we look at this adjacent point over here, it is the superpositioning of a crest and a trough. Again, a crest and a trough, you get a destructive interference. So if you look closely at any red point, let's take this red point. You can see one dotted, one dash. Now one dotted and one straight matlab kya? You have a crest and a trough. Again, destructive interference aaya. So this is how you get an interference pattern of a light. So whatever blue part or the blue dots you have, there the intensity is high. So we can call it as a bright point. And whatever red dots you have, the destructive interference, the intensity is low, or we can say zero. So we can consider this as a dark band or dark spot. So again, here we will have dark, and again here we will have bright. So now you can see what exactly is interference pattern. It is simply alternate bright dark bands which we will be able to see on that particular screen. Clear? Any doubts in this? Bolo yes or no? Okay, good. So moving forward, now let's understand the interference of light a little bit in detail. But before we actually understand what happens in case of interference of light, again, I have a GIF over here, so this may be probably better understandable for you. I'll erase all the doodling which I have done. So this is how the constructive and destructive interference it basically forms. You can see over here, once again, I'll try to pause it. Once again, you can see over here, the amplitude has almost doubled, obviously, provided that both the waves have same amplitude. Here, the amplitude becomes almost zero or exactly zero, provided both the waves have same amplitude again. So you have a crest and a trough, becomes zero, a trough and a crest, again zero, so on and so forth. Now, let's go into details of interference. Okay. Now, in order to see interference, now generally what happens now, this phenomenon obviously we have never ever seen in daily life. Now, in daily life, we are not able to see an interference pattern formed anywhere on our walls or on bed sheets or something like that. So why is that? Because it's a specific phenomenon. It's a special phenomena which needs to be properly seen. Now, if we want to see a proper sustained interference pattern, what we need, obviously we need multiple sources, preferably two proper sources of light. And these two proper sources of light which emit waves at a specific frequency, a same frequency, and the waves which are emitted, they should be in phase, or at least should have a constant phase difference between them. So if we have such a wave, such a waves which are traveling, then and then only we are able to see that interference pattern. And the sources which emit light like this, they are called as coherent sources. So we are going to understand what exactly do we mean by coherence. Now, when we say that two sources are completely coherent, when they have constant phase difference and same frequency. Either they should have same phase or they will have constant phase difference. And obviously both of them should have same frequency. So in order to see a proper interference, we need to have coherence in the sources. If the sources are not coherent, then we won't be able to see that interference pattern. Now, when we say the sources should be coherent, additionally, what things do we need so that the proper interference pattern will be visible? The additional things, obviously, they should have same frequency, they should have a constant phase difference or same phase. Apart from that, they should have same wavelength, and most importantly, they are independent of time. They're not dependent on time. So it should not happen that they're coherent for certain amount of time. They should be coherent all the way, no matter what. Now coming back to the point, now why we are not able to see interference on daily basis? Because the most important things, the sources which we have are not coherent sources. The sources which we have are non-coherent sources, always. That's why even though a lot of light is interfering with one another, we are not able to see a proper interference pattern on daily basis. Because of this particular condition that the sources are not coherent. तो कोहेरेंट सोर्सेस बोल रहे हैं हम लोग कब से, कोहेरेंट सोर्सेस, तो ये कोहेरेंट सोर्सेस होता क्या है एग्जैक्टली? So the coherent sources, it looks something like this. Okay, so this is the diagram of what coherent sources it means, and obviously the additional part which we have, incoherent sources which we have. Okay, so the best example of it is a laser. Laser is a coherent source, perfectly coherent source, because obviously it is amplified and stimulated light. Okay, and the light which we use in daily basis, LED hoga, which is most common now, tube lights hoga, or the lights which we have, flashlights hoga, whatever it may be, the source is incoherent. Now we will be probably revisiting why it is incoherent in photoelectric effect, but for the time being, just to have a proper comparison, what is coherent and what is coherent means and what is incoherent means. Okay, so once again I have another picture as well which actually gives you an idea, proper idea. While laser is a coherent source, because we know that's unidirectional, it goes in the forward direction only, and a specific wavelength of a specific color. रेड लोगे तो सिर्फ रेड ही आएगा उसमें से, ग्रीन लेजर then you'll have only green color which is of single wavelength. But in case of a flashlight, it's a white light.